Hi, welcome to Unit 59. Unit 59 talks about basically the HR diagram. And this is actually a very, very important tool that astronomers use. Remember, leading up to this unit, we were using all kinds of techniques trying to find the size of the stars, the temperature of the stars, using Bean's law through spectroscopy, using the luminosity of the star, the brightness of the star, the mass of the star. So now you gather a lot of information. Imagine that you have binary systems and gather a lot of information. So basically, when you put them together, it seems like there is a pattern, and that's basically what this is. So the pattern becomes now useful down the road when you have a new star, or at least you would want to compare a star to a specific class of stars. So that's basically the usefulness of this diagram. Okay. So again, we're going to look at this diagram and see basically how stars line up, and then describe the mass properties, describe the luminosity and all of the properties of the star using this classification. Again, as I was saying before, we used all kinds of techniques up to this point, and then when we put them together, actually Hertzsprung and Russell basically put this thing together, they came up with this classification, okay? And it's a kind of a genius because of the fact that you have on one axis, you have the temperature. Note that the temperature is actually goes from high to low, okay? So you would expect on an x-axis, if you're putting things in a Cartesian coordinate system, to go from small to high. This one is actually the opposite, okay? And you will see the how clever that technique is, and then the luminosity on the y-axis. So that's basically what this diagram look like. So again, it seems like the stars fall into groups. Basically, the bulk of the stars, they fall in this axis that spans from low temperature, less dim stars, all the way to high temperature. Remember, the high temperature is on this side, and then super bright stars. Okay, so these are main sequence stars. And then there is a bunch of them that have low temperatures. Note that this temperature is about 3000 Kelvin versus, for example, this one, which is 30,000 Kelvin. So you have low temperature stars, but they're super bright. Okay, hence they're red giants or maybe blue giants. Okay, so this is outside of this main sequence classification. And then you have another category that is actually less dim, not as bright. You wouldn't see it with the naked eye. You wouldn't see them, but they're super hot. So that means that they are small. Hence, white dwarf stars. Okay, so this is the main grouping. So we have three main sequence stars, red and blue giants, and white dwarfs. Okay. If you look up close to this system in here, so you have the main sequence stars. You have the red giants. Those are red because they're less temperature on their surface, but they are super bright, super big. Okay. And then you have the yellow giants that fit in between, just where the sun is, it's a yellow star. And then you have the blue giants, which are actually super hot. And one of them is Rigel, actually. Rigel is in the Orion Nebula. Rigel is a big star that you can see every night, especially in the winter, okay? In here, at least in the northern hemisphere. And then you have actually Betelgeuse that you can see, Aldebaran also that you can see easily. Betelgeuse is part of the same constellation, Orion, and Aldebaran, which is part of the Taurus. So you can see them, okay? In the winter at least. Procyon, you have Procyon actually, so you have some famous stars in here that you can see. First of all, you have Proxima Centauri, the closest star from us. You can see it's super, super dim star, 1,000 that of the sun, but its surface temperature is about 3,000 Kelvin. Okay, so that's why it's a dim star. Then you have some of the stars we mentioned in previous units, the Proxima, the Centauri system, Alpha Centauri A and Alpha Centauri B. One of them is slightly brighter than the sun. Actually, you see the sun in here, and the other one is slightly dimmer than the sun. Okay. You have also Ceres, which is the brightest star in the night sky after, of course, the sun and after the moon and after so those are planets. So I mean, like Venus, for example. But this is the brightest star in the night sky series. But it has another partner. So this is Series A, which is a main sequence star, and it's hotter than the sun. But you have another series in here which is far hotter in temperature, and it's actually part of a binary system. Same thing with the Procyon. Procyon also is a binary system. You have Procyon A and Procyon B, and they are almost the same temperature in here. Okay, but one of them is super bright compared to the other one, because the super bright one is a main sequence star, and the other one is a white dwarf. And then you have these main sequence stars. Again, you have the red giants, you have the yellow ones, and here is a classification that we have the spectral classes that we have seen before. O, B, A, fine, girl or guy, kiss me. So this is basically based on the temperature. So the temperature in here on the x-axis and the luminosity. Note that the luminosity is actually on two things. First of all, is as compared to the luminosity of the sun. So the sun has luminosity 1. A star that is 10 times brighter is sitting in here. And that's the second point I want to make in here. This is actually logarithmic scale. If we were to do a linear scale, we wouldn't fit it on the screen in here. It would not fit because of the fact that this would be 1/10,000th of the luminosity of the sun, and this would be 1 millionth, not 1 million, a million times brighter than the sun. So they wouldn't fit on a piece of paper or a screen like this one. So this is a logarithmic scale. So same thing in here is actually a logarithmic scale too. Okay. So that everything is concise in there. So this scale sometimes, at least the HR diagram, sometimes is misleading because it looks like it's linear. Because we have, at least in our visual, we see things linear, but it's actually a logarithmic scale. It's actually far more than what you see in here. Okay. In terms of size, again, you have to look at it at the diagonal in here. So again, this is the sun's radii, and these are actually a lot smaller than the sun. Of course, that brings me to the white dwarfs being super small, compared to, for example, Betelgeuse, which is the biggest star that we can see up close in here, in this diagram in here. But the Betelgeuse being super big is not that hot, relatively speaking, compared to the sun, for example. Okay. But because it's super big, it's super bright, you can see it easily in the night sky. Another thing in here that has to do with the masses. The masses also is another important aspect to it in here. These are the main sequence stars. The less massive stars are less bright than the more massive stars. This is 20 times the mass of the sun. So these are the main sequence stars. They have their own rules, and actually very nice rules that you can follow. But the oddity in here is in this ones in here. These are actually big stars also in general, masses, but they are actually less temperature. So it's kind of, they are actually not burning hydrogen in their core. So that's really the main difference in here. These are still burning hydrogen in their cores. This one going through other processes. This one are not burning anything. They are just relic heat from when they were stars, and now they are basically they exhausted their stellar stage, and now they are actually toward the end. They are not burning any. They are not fusing anything to anything. They are basically dying. Okay, so these are the red, the white dwarfs, and their masses are ranged between half the solar mass all the way to about 1.4 solar masses. Okay, there are restrictions on why that has to be the case. Okay. So this is the graveyard of the normal size stars. Graveyard for the big stars is a different story altogether. They're black holes and actually neutron stars. Okay, in terms of masses, there seems to be a connection between the luminosity also and the mass, and this is through this relationship. The luminosity is basically proportional to the mass to the power 3/5. If we express things in terms of the solar masses, so m is actually in solar masses on the x-axis, and the luminosity is actually on the y-axis in terms of how luminous the sun is, then in this case it's an equality. Okay. For the most of the stars, except when it comes to the small stars, there is an exception to that. Okay, so the rule does not apply. So again, the HR diagram has a lot of information. Now, stars are, I mean, at least based on this HR diagram, stars are classified into 5 groups, okay? You have the 1A and the 1B, and those are the bright supergiants or the regular supergiants, okay? Again, these are brighter than this region. Again, this axis is the brightness, okay? How luminous a star is. So you have 1A and 1B. And then type 2 stars or class 2 stars, and those are bright, again, giants or the regular giants. So I'm sorry, star 2, class 2 is bright giants, and the other one are regular giants, class 3 that is. Which brings me to the class 4, which are the subgiants, and that's why they are less luminous than any of the others. But they are all outside of the main sequence stars. If you're taking the lab version of this class, you will see that this is very, very important when you're looking at the spectral types of the star, and you determine, first of all, what class it is. Then you can use, if it is of a class 5 in here, some of you guys in the lab, they call it class V. It's not V, okay? It's class 5, okay? So we're using the Roman numerals in here. So again, these are the main sequence stars. So they have their own rules, and we can easily determine a lot of their properties, okay, based on what we know about this stars, okay. Again, at this point, these are now you might call it class 6. Nobody calls it class 6, but these are the white dwarfs that are out of the classification. They're not even stars at this point, okay. They have, they are stars, but in terms of their source of heat is not the same, okay? They're not burning, or they are not fusing any kind of elements, whether being the lightest of the two, namely hydrogen and helium, or any of the subsequent elements in the periodic table, okay? Again, these are the stellar luminosity classification in this case. So you have 1A and 1B. Those are the bright supergiants and the supergiants, including Betelgeuse and Taurus. And that's from the Scorpion, basically, constellation. And then you have Polaris, which is actually a big star, but it appears dim compared to, for example, even some of the main sequence stars, because of the fact that it's super far away, okay? So it's a bright giant, class 2. Class 3 in this case are ordinary giants like Arcturus, okay, which is in the Boötes. And then class 4 subgiants, and that includes Procyon A, okay. And finally, main sequence stars that include the Sun, Sirius E or Sirius A, and also the two, or at least the 3 Alpha Centauri, the 3 Centauri system, namely the Alpha Centauri A, the Alpha Centauri B, and Proxima also. Anyway, so this is a lot of information that we have had, basically based on the studies we did before, and how Hertzsprung and Russell basically put these things together in a nice diagram. Thank you.